Welcome, everybody. Thank you for being here this early in the morning. This is amazing to be up here and see this. When I was a teenager, I always wanted to be a rock star, and I think this is the closest I'll ever get. So that's very, very cool. I'm Nikolai Parlok. I'm a Java developer advocate at Oracle, and today we're going to talk about Java 24 and then whatever else we can get to. So let's just get going, because there is a lot to talk about. And what? That didn't just happen, right? Oh, my God. Imagine working with pros for once. I don't even, what? It'd be a great time to be reminded by macOS that I have to update the. We'll get there sooner or later. There we go. OK, whew, good. Thank you for sticking with me. OK, so we're going to focus on Java 22 to 24, but 24 already has a decent chunk, and then there are a few other things I need to tell you, and then we can see how far we can get. This is really just a showcase. If you want to use these features in production, you can either just go ahead and do that, or you could also look at the Java YouTube channel, at the documentation or anything. I cannot really give you a tutorial on all of these, because that would take even longer. The slides are already online if you want to follow along, and you can ask questions at any time. I know we're in Sweden, so that's not super common, but you can. And I will later ask you to yell loudly, so mentally prepare yourself for that. I'm going to go over these 4 things, definitely. AOT, class loading and linking, less virtual thread pinning, stream gatherers, and the class file API, since these are all features that became final in 24. Then we have a few more that became final in 23, and then 22 as well. And we can dig around and see in those what we'll find there. And then we have some preview features that we could talk about. 3, there are more, actually, but these are the 3 that I prepared. And then the one at the bottom, which is no longer a preview feature, but sometimes people are curious why and what happened. So we could talk about that as well. But for now, I just want to get started. Let's talk about AOT class loading and linking. There we go. OK, so Java has great peak performance, but some of the downsides of Java performance characteristics are that it has a slow startup and a slow warm-up time. So what are the difference between those two? Startup is the time from the Java launcher launches all the way to the first statement in your main gets executed. So it's the first time it does anything useful. And then from there to peak performance, that's warm-up. And those things can take hundreds of milliseconds, maybe seconds, in rare cases even longer. So it can take a while to get all the way to this pretty good peak performance. And Project Leiden came up to change that. And so what it wants to do is to try to find this early work that the runtime has to do and try to put it somewhere else. So class loading, call side linkage, constant pool resolution, interpretation. There's an N missing at the bottom. Can we do all of this ahead of time? So really the goal is basically just AOT all the things. Do everything ahead of time, so that in that perfect universe, the first thing that happens is your first statement at peak performance. Of course, that's far way off, but that's the goal. That's the thing where this is heading. The issue with this is that Java is very dynamic. That means while we think of Java as a static language because it's statically typed, a lot of things are happening at runtime. So what classes are loaded, classes can be redefined, how they are linked, access control, so which code can see which other code with modules in between, right? You can have command line arguments that say, well, this is internal, but I allow an exception for this time. All of that only happens at launch time. It's only visible at runtime. So this cannot really be done ahead of time. You'd think, how would you AOT all of these things? And ideally, we have a crystal ball, right? Ideally, we have something that tells us, for this code, this is what will happen during startup and warm-up. And so we're going to do all of that now at build time, so before we deploy the application. We don't have a crystal ball, unfortunately. What we do have is training runs. We have a way to observe something in practice and then draw conclusions from that. So this is where the AOT cache comes in. Project Leiden, which is one of the, I would say, the 6 biggest JDK projects that are currently going on, introduces this. And so the idea here is to observe the JVM while it's doing something, and then capture all of those decisions in an AOT cache. And if you have used CDS archives explicitly, you might know that name, and it's a continuation, an expansion of that. If you're on Java 17 or newer, you definitely have to say the CDS archive, at least implicitly, because it's already helping you boot faster. And then the idea is that we use that as the initial state for the future run. But, and this is crucial and really cool, that the JVM will still see whether this cache is valid. And if it doesn't, it will invalidate things. It can still de-optimize. So you then pay in the sense that you don't get the performance boost, and you might even get some longer time to warm up because of some de-optimizations. But you will always get correct behavior, right? So you will not be in a situation where the AOT cache did something that now doesn't apply anymore, and then it radically misbehaves at runtime. Java doesn't do that. So the worst case is you don't get the extra performance boost. And this is what this looks like in practice. So this is at the moment the process. This process will probably be streamlined in the future. It's still very early days in this. So the idea is that you launch your application. So down here's the class path or the module path maybe. You launch your application here, and you set the AOT mode to record and give it a configuration to create. And then the next command is the assembly phase. It does not launch the application. It just launches launcher, says, here's the configuration. Please create this cache. And it will. So we'll create this file. And then in production run, you just say, well, here's the cache. Please use that to run. And so the first thing that Leiden puts into this process, into this training and caching process, is class loading and linking. So the goal here is to improve startup time by making the classes of an application instantly available in a loaded and linked state when the hotspot JVM starts. So that's the thing that's already working in 24. And then there are a lot of, on the list that I showed earlier, AOT, all the things. There are plans to go further into this list and do further things in the future, but that is already available in 24. And just some superficial benchmarks. This does not mean that your application will get 40%, might get more, might get less. The point is just to prove it's worth looking into it if boot time is something you care about. Spring Pack Clinic got 40% faster. And just as a ballpark number, that specific AOT cache is 130 megabytes, and the Spring Pack Clinic does use a decent chunk of Spring, so it's, Spring is not exactly known for being like super slim dependency tree. So you can probably have a gut estimate what that would mean for your application. So there are some limitations to this. If you do have this AOT cache, then you will have to run on the same JDK release and hardware and operating system. The class path or module path that you use for training and for production needs to be consistent. What exactly that means, you can think of it, it must be the same for now, but in detail, it's not quite that strict. The JEP already explains that. I'll give you a link later. Module options have to be the same, and JVM TI agents can't do all the things they are able to do, because otherwise they can redefine classes, and that wouldn't work. But if any of these conditions is not the case, then the AOT cache is just ignored. And as I said earlier, you will just not get the improvement, but it will still behave correctly. And what we'll probably see in the future, let's stick around here for one moment. What we'll probably see in the future is further things to put into the cache under these restrictions or limitations. But then maybe in the future, you'll be able to accept additional restrictions selectively. You'll be able to say, you know what? This is something that the JVM allows, but my program doesn't do. So I'm willing to accept that the limitation that this is not allowed to happen at runtime. And there could be a whole set of those things that you can accept. And then the assembly runner can decide, OK, given these limitations, which things make sense to put into the cache. And obviously, the more limitations you accept, all the way possibly in the end to like a closed word assumption. Or even further, you could accept that the configuration you ship with your application actually doesn't change. So we could think of a version of this feature where all of that XML parsing that you need to do when launched to get your configuration, even that could be restricted. You would be willing to say, that's not going to happen at runtime ever, because I'm always shipping with exactly the same configuration in the Docker file. And then even that could potentially be cached, although that's very far down the line. So you accept in the future probably more restrictions, or you can accept more restrictions, and then get even better performance out of that. And that performance improvement is emergent. You don't have to pick this improvement and that improvement. Just say, these are the restrictions I'm willing to accept, and then Java is going to give you the best outcome for that. If you learn more about this, JEP 483 is the one that introduced this, and then we have a short little Inside Java newscast on that as well, so you can look into that one. Okay, if you have any questions, you could ask now, or we could just keep going. Looks like keep going. I can hardly see you, so you would have to yell. Okay, so let's talk about virtual threads and pinning. I will assume that most of you know about virtual threads, or actually I will assume all of you know about virtual threads. If that is not the case, don't feel bad, it's a short section. There was a great session about this yesterday morning. Maybe you can rewatch that one, but also on the Java YouTube channel, there's lots of content on that. So virtual thread is a regular thread, has low memory footprint. It's basically just the stack that you always have and then some bytes, small switching costs. It's scheduled by the JVM, blah, blah, blah. The important part is it waits in memory, and no expensive platform thread is blocked. Now, there's a little caveat there. That's not entirely true. There are a few cases where this desired behavior does not actually materialize. And there is a difference between pinning and capturing, but I will spare you the detail. In the end, the effect is that you end up in a situation where you would hope that the virtual thread waits in memory for free while a platform thread is doing other things. But in these situations, that wouldn't happen. So there are situations where this unmounting doesn't happen. And that can be caused by object monitors, native calls, class initialization, and file I/O. And this is fixed for one of them, object monitors. We're going to look at that in a second and what that means. Native calls, this is theoretically fixable, but a lot of effort for very questionable return on investment because it's rare that this happens. Class initialization, there will be work on that. That will probably also no longer pin. And then file I/O, that has to do with JVM and operating system limitations. This is probably not going to be solved for now either. But let's look at object monitors. So object monitors, by the way, if you don't know, if you call object.wait or notify all, or if you use synchronized blocks, then that you're interacting with the object monitor system. With the object monitor, I should say, probably. Right, and so the original implementation was bound to OS threads. And changing that just required a lot of work. And so the decision was made back in when Java 19 previewed virtual threads and Java 21 finalized them. Let's not keep this feature hidden until we have fixed this. Let's put the feature out there with this known limitation. So we talked about that back then, that you should look into avoiding synchronized for that reason, or rather you should avoid blocking operations within a synchronized block. But this problem now went away as expected. So within JDK 24, all interaction with the object monitor does the proper thing. So one big chunk of the reason why virtual threads might not have worked out for you the way that you hoped they would is now removed. So if you tried virtual threads on JDK 21, say, then and you didn't see the performance improvement that you were hoping for, the throughput improvement that you were hoping for, there are a host of reasons why that could have been the case. This was one of them, and this is now removed, so you would try again. But there are also reasons, just the performance characteristics of your application. Virtual threads aren't magic, so they're not going to help everybody. But yeah, so if you have a web backend specifically or some other application that does a lot of concurrent blocking, basically, so a lot of things happening at the same time, and a lot of those things are blockingly waiting for something else, then look into virtual threads and give it another try if the first one wasn't that successful for you. If you want more, again, there's a JEP on that. JEP 491 introduced this fix, and then I made a video on that as well, going into a little bit more details and also explaining, I think, if I remember correctly, what's up with file I/O and IOU ring. Okay, let's talk about something that you can actually actively interact with while writing code, because that's, for me at least, the most fun features. I have a clear hierarchy, language features most exciting, API changes, and everything in the runtime is pretty cool that Java does all that, but I'm more like a language and API kind of geek, so I'm really happy about stream gatherers. Let's talk about streams in general. Streams are pretty cool, but they're not like, they don't have like every possible intermediate operation under the sun, right? Remember, a stream starts with the source, then has a bunch of intermediate operations, map, filter, flat map, whatever, and then there's one final operation. And in this intermediate block, it has a lot, but it doesn't have literally everything. Sliding windows, fixed groups, you could do a take while that includes the one element that failed the predicate. That's actually pretty handy to have that one. Scanning, you can have increasing subsequences. There's so many things that you could think of that it would be ridiculous to put all of that into the stream API, because probably most people would then end up using just like 10%. Honestly, already I think most stream intermediate operations are barely used, because map and filter get you very, very far in real life. Okay, so we had this problem before, or rather, it was not really a problem, but a situation where terminal operations are likewise, a lot of them you can imagine, but also Java doesn't offer all possible terminal operations for streams. What it instead offers is a mechanism for us to plug into that. So we have this concept of a generalization of terminal operators, which is called a collector. Then we have a few implementations of those, like collectors to set, collectors to list, which you're probably not using anymore if you're in JDK 16 or Neo. You're just writing to list at the end of the stream. Not exactly the same behavior, but actually the better one because of immutability. Anyway, so collectors to list, not used that much anymore, but you probably know collectors to map as well. There are a few of those there. So you have this concept of a collector. You have some implementations, and then you can pick one of those implementations or create your own and put it into stream.collect. And now we're doing the same for intermediate operations. So the gatherers API consists of a new concept called gatherers, which basically are kind of like a collector in the sense that they take every element from the stream, but these ones push further elements out to the next operation because it's an intermediate operation. Then there are a few implementations that exist. For example, gatherers.scan is one of them. And then you have an extension point, stream.gather, where you can plug them in, and it will then look like this. So I have a stream of ABC and some ACFBS, and then I call gather, and then this is a static import of the gatherers.scan method. So I can give scan. Doesn't really matter what scan exactly does. It's an operation that the original API didn't have. And then I say, OK, so this is an intermediate operation, so I then keep going, or in this case, I just put a terminal operation there. So let's look at how these gatherers work and how you can implement your own. So gatherers have 4 building blocks, but only one of them is required. And the one that's required, it's called the integrator. The integrator takes as input a state, so you can keep state from one operation to the next. It takes in the current element of the stream that's being processed, and it takes in a downstream. And you can think of downstream as the rest of the stream pipeline, the next operation below, like the next intermediate operation, or maybe it's a final operation. So what you want to do is you want to take an element, you want to look that up and see whether something with a state, maybe there's some interaction with a state, you could update the state, or maybe you don't even have state. That's actually quite common as well. And then you can decide to push this element or anything really down into the downstream. You don't have to emit anything. You can emit something entirely different. That's up to the operation you're implementing. So let's create a no-op gatherer. So there's a lot of generics. Just trust me that they work out and ignore everything in the angle brackets. It makes it easier to read. The really important part is this one here, where I say my integrator takes a state that I'm not using. So I'm using the underscore to say it's an unnamed variable. I don't need that. The element and the downstream, and then I just push the element downstream. That's all I'm doing here. I'm taking an element, pushing it downstream. So this is a no-op. Nothing really happens here. And then I return a gatherer of this integrator. That's basically like the hello world of gatherers. Super boring, though. So let's do something slightly more interesting. Now we're going to re-implement map. And if you do want to use the gatherers API to create your own gatherers, which is a lot of fun, I can highly recommend to just go through the list of intermediate operations and re-implement them as an exercise. Re-implement map, re-implement filter. It's a fun way to get used to the new API, and it's really easy to validate that this actually works. So what I'm doing here is I'm again taking the state that I'm not using, the element and the downstream, but then of course I have to apply the function, right? It's a map, so the function has an input. So this lambda captures that function, applies it to the element, I get out a new element, and then I push it downstream. Pretty straightforward. And if it would be a filter, then there would be an if that predicate tests is true, then push downstream. And you need to return something here, by the way, also previously as well, because the downstream might say, I'm already done. I want to have only the first element, for example. So the downstream can signal, I'm done, I don't want to continue, and then you should should return that information upstream, basically, so the stream pipeline stops early. But that's the implementation detail. You'll see that when you go through the documentation. OK. What are the other 3 building blocks? Now, let's say we want to do something with state. Now we need a way to get empty or initial state. That's one thing. And then the integrator, I said, interacts with that state, but we already talked about that a little bit. We'll see that in practice now. Then we have a finisher, which is maybe the most important part about gatherers, because you could hack your way through some of these things in the past, and you could do some of the operations that I presented. But the problem was that when the stream ends, you didn't get a signal that the stream is now over, because for some operations, you need to do something after the last element, and you couldn't get that signal. So that's why many operations weren't possible. So the finish is important. It tells you, we're done now. Here's the last state you have. Here's the downstream. Do you want to do anything else? Is there anything else you need to do? And then you can, and we'll see that in practice as well. And then we have the combiner, which you would need for parallel streams. So if you use parallel streams and your gatherer should be used in parallel, then streams they're split up, but then eventually they're combined. The results are combined. That's what you need the combiner for. We're not going to look into that one, so we're just going to have an initializer and a finisher. Because what we're going to do is something that's inherently sequential. And I personally discovered that most gatherers I'm writing are sequential. Like this one, I want to have groups of 2. I want to take my stream of 5 elements, and I want to have the first 2, the next 2, well, and then the last one, really, right? So this is something where it fell apart. If you didn't have a finisher before gatherers, if you hacked your way through all of this and tried to implement this yourself, you couldn't get the last element out. So now you can. So we're going to look at how this works. We're going to need an initializer that creates an empty list, so you can start collecting groups. And then we need the integrator to add something to that list. And then when the list is full, we emit that list. And then in the end, a finisher that says, OK, we're done now. And let's emit the last group. So let's go through each of these three things we're building. Initializer, super easy. It's a supplier, and we want to collect elements in a list. So ArrayList new creates us is that function. All right, and it's a function. You don't create a new state, actually. You give a recipe of how to create the new state, because again, this could be used in parallel, theoretically, and then you need to create like a bunch of states for each thread first, and then later join them. Okay, so super easy, create a new array. This is how to create a new state. And now we're doing the integrator. So again, we're taking an element and the downstream, but this time we're also taking the list, right? This is the state that we kept ignoring before. And then you add the element to the list, you check whether it's the right size, and if it's too small, we just keep going. And if it's full now, we create a copy, we push the group downstream, and in between, we change our mutable state. So you can see that the state is mutable here. We add it to the list and then eventually clear it. And once it's full, we create an immutable copy and push that downstream. This is very important. Do not push the state downstream. If the state is mutable and you push it downstream, the downstream might change the mutable state, and this will go horribly wrong, right? So if you have something that is mutable, like a list here, you need to create an immutable copy of it. Well, you could create a mutable copy of it so it doesn't have this interaction, but better yet, create an immutable copy, push that downstream. Okay, and then the finisher is the thing that runs at the end, and it will just take the last list and just create a copy and push. This is actually kind of buggy, I realize right now. I didn't update the slides after I found that bug. Does anybody see the bug here? Yes, perfect. So here I'm saying, oh, I reached the right number of elements. Let's create a copy and push it downstream, and let's clear the list. And here I'm saying, push the list downstream. It might be empty, right? If I have 4 elements and I make groups of 2, I end up with an empty list downstream, which is not what I wanted. So there should be a check here that says, do I need to emit this? If it's empty, I don't. So yeah, but the overall structure holds. So this is how you create the finisher. And then you would do this in a method like this. You would have a static helper method somewhere probably in your gatherers, util, or whatever you want to put it. There's already an open source project I saw the other day, which published a bunch of gatherers. I'm going to look at that, and I'm probably going to contribute mine if I get around to that. And this is what it would usually look like. So you put that static method somewhere, you give it a nice name. Think of it as something that, like terminal operations, you would probably, or like the collectors, I should say, you would probably make a static import of, right? So give the method name really something that speaks on its own, in this case groups, which gets a size, and then, you can see this, I create the initializer, the integrator, the finisher, and then I do a gatherer of sequential, put all of that in, and then this intermediate operation that I'm creating here will signal to the stream pipeline, I'm not parallelizable. So if the user says parallel, screw that, I know better. So you want to get sequential stream anyway. Good. This is how we'd use it. As I said, with a static import, and then the output would be AC as a group, FB as a group, and then S as a group. And as I mentioned, if S is empty, the code that I showed you will actually have an empty list at the end, which is not intended. Okay, JEP 485 is the one that introduced this. Victor Klang, who was the guy behind this, gave a cool talk about that, which is linked here. And then we made videos about that as well. So you can go into that. I think my colleague Jose made this one, Better Java Streams with Gatherers, recently. And I think he has a follow-up that goes even deeper, like master class or something. Go to the Java YouTube channel, you'll find it there. If you have, in total, I want to say, 2 or 2.5 hours to spare, you'll know way more about stream gatherers after than I can tell you. But also, it's a fun API. It's easy to experiment with, so I can highly recommend just trying it out. It's pretty cool. It's final in 24, so you can use it and rely on it never. Backwards compatibility as usual, probably not changing ever. Okay, last one we have to do before I get to my surprise content. That's the class file API. I'm not going to go into the details of the class file API because few people of us will interact with it, but I want to show you why it's important that it exists. So let's talk about bytecode. Bytecode is the instruction set for the JVM. Justin Lee had a talk about that, right? Is that in the future or in the past? It's after lunch. So if you want to learn more about bytecode basics, Justin Lee down there will have a talk after lunch. And then you will learn way more than I can show you on this slide. But basically, it is the instruction set for the JVM. Create objects, create an array, invoke a method. All of that is, in bytecode, enshrined in bytecode. And the basic life cycle would be this. Java-C reads the source files, creates bytecode, dumps them into a class file, and then the class loads it, parses it, verifies it, right, so that I can manually write bytecode or class files and then I could maybe trick the JVM in doing something that it shouldn't, but I can't because the class loader makes sure of that. And then in the end, the JVM will execute it. Those are the basics. But Java's reality, once again, it's a very dynamic runtime system. It's much more complicated than that. Frameworks will generate bytecode at compile time, at build time. The just-in-time compiler or ground-native image may turn it into machine code. The AOT cache we just saw might prefetch it and dump it. JDEPs, spotbugs, those are tools that work on bytecode. Agents, libraries can manipulate that. There's probably more that I didn't put on this list. So the simple life of bytecode is much more complicated in practice. And while few of us do this directly, we still often do this. So I made a little bit of a graphic here. So to introduce you to this is supposed to be the bytecode, basically. This is the class file. The class loader interacts with the class files, and then Java C, JDEPs, they all work on class files too. And this is a runtime representation of the bytecode, which is where agents and libraries can come in and interact with that. So there's a lot more going on than this simple example. And the way that these tools do that is usually not on their own. Most of them don't manipulate bytecode themselves. They use one of a few tools. And one of the biggest players is ASM or ASM in this game. Either it's used directly, or even tools like ByteBuddy or CGLib will work with ASM under the hood. So ASM is, as I said, like a big player in this game. And Remy, who's maintaining that, is doing an awesome job at keeping it up to date. But that still has some downsides, and I want to talk about that next. And that has to do with the bytecode level and migration in general. So this is all a topic that relates to migration. Let's talk about why. So the Java language evolves, the JVM evolves, and so it's entirely possible, and happens occasionally, that a new Java version introduces new features, and then an old JVM can of course not run that. You all know that, right? You've all tried maybe accidentally to compile with JDK 21 and then accidentally try to run on Java 17. This will not work. You will get a complaint about something bytecode level. That's what this is about. The compiler will embed its own version as a number in each class file. So for Java 21, that number is 65. And then the JVM, but also all of these tools, ASM leading the pack here, will look for that bytecode number and will say, oh, well, that's a bytecode number I didn't know, actually. So all kinds of things might be happening in this bytecode that I don't know how to deal with, and so I won't work with this. Which makes sense, right? You don't want your tool to be just guess and hope that it will work. But the problem then is that this can block updates. So let's say you have a dependency tree and everything works at 21 and it's fine, and now you want to switch to 25. You compile with 25, you end up with bytecode level 69, and now ASM and all these other tools will say, I can't work with that. And that leads to like a chain upgrade. This is a dependency tree of your regular web application. And what I wanted to do is, I wanted to update to Java 21. So then I get new bytecode, which is now new level 69. And this is the yellow part is what I needed to update. But then the old ASM wouldn't be able to do this. The old ASM would be like, no, I can't work with 69, so I need to update that. But that's part of a larger dependency tree, so I need to update Spring Boot. And then all the other dependencies upgrade. And ideally, you should be able to update those independently, right? Like it's not the end of the world that this is the case, but it's not really great either. So this situation is one of the big reasons why I keep telling people if you update the JDK before you need to update all of your dependencies. Keeping dependencies up to date is a good thing to do anyway. Brian Vermeer surely has a talk somewhere around here. Actually, I think he has it right now, where he talks about the importance of keeping dependencies up to date, for example. But like in general, that is good to keep dependencies up to date, but also you need to do this for updates. And it would be nice if those concerns would be a little bit more orthogonal and less like if you want to do the one, you really should do the other first. And the way to do this is to create an API that manipulates bytecode and put it into the JDK. That means that then we have a stable API within the JDK that can be used, and that will, of course, always be up to date, right? If I update from Java 21 to 25, then the new, well, in 21 the API didn't exist, but you get my point. Let's say from 24 to 25 then. Then, I have the new version of the API, and the new version of the API can, of course, work with the new bytecode. Now, depending on what the tool does, this might still cause problems, because it might still become a situation where it says, okay, I'm getting if you visit the bytecode, I might still encounter instructions that I don't know, or constant pull entries or whatever. But those cases are not that common. Like this, I don't know this bytecode level, I'm not going to do anything, is definitely the safest way, but it isn't the only way. The way that the Classfile API basically picks is, look, I'm going to give you everything that's in that file, and you pick what you care about. And if that part that you care about changed, then we're in a problem, probably going to see a runtime exception. Then you probably still have to fix it and make updates. But in many situations, that's not the case, right? Like a dependency analyzer doesn't need to read, all the entries of the full class file, for example. So for most use cases, it's actually okay that if the bytecode level updates, as long as the API can still deal with that, it will not see these changes because bytecode is not actually radically changed from one release to the next. And ideally, this would be the situation you're in. You update to Java 25, you get the new bytecode level, but the class file API is part of 25, so it can deal with that, and your application uses that, and then it's all good. So that's the long-term goal here. Java 24 introduced this and finalized this feature. It's now up to all the projects that do bytecode manipulation to look at that and hopefully find out that the API does what they need, and then slowly move over to that. I have a talk linked here from Brian Getz about the class file API for the JDK, and then I made a video, but that pretty much just says what I just said, so no need to watch it unless you forgot something. And so the goal is that hopefully these libraries will move over in the next couple of years, and then at some point we'll be in a situation where ASM isn't needed anymore. And nothing against Remy, who's working on this. I think it was at that JVMS talk, actually, that I'm linking here, where Remy was in the audience, and Brian basically confirmed with him that he has done a lot of work in ASM, and he's kind of happy to spend time elsewhere as well. So I think it's a win-win. OK, good. Now, I talked about a lot of cool things you're going to get. Now we're going to take a few things away from you. Just, it's a little bit of a give and take. A lot of give, a little bit of take. Well, you're also getting something in the take. Oh, we'll get there. So if you are using any of these technologies, you should stop. They're already gone in a release after yours. So let's say you're on 11, and you're relying on RMI activation. Not a good decision. Like the next update to the next version with LTS, from your point of view, that would be 17. It's already gone. Using the security manager, and I'm going to talk about that in a second, that's now also gone. So these things are already removed. So, time to change course if you're still using those. Let's talk about the security manager specifically. What is it? It's a system of checks and permissions. It's intended to safeguard security-relevant code sections, and it's embodied. It's not the only part, but it's embodied in the type security manager. There are other parts of this, but this is like the important moving part, basically. What you need to know is, right now, that it's barely used, but maintenance intensive. So the barely used, I just want to ask the audience, who of you has in their code base a call to security manager? Just let me, yes. OK, good. It might happen indirectly. It might happen on your behalf. But if you've never seen this, it's very unlikely that's the case. So that's good, right? So you're all not impacted. So I'm not taking anything from you. But what you're getting is less maintenance work being spent on this, which means OpenJDK can spend that time elsewhere and can work harder on other features. Maybe finally somebody pushes up Valhalla. Don't tell Brian I said this. So the security manager is already disallowed by default since JDK 18, and in 24 it's removed. So if you are going with each 6-month release, you will know this. You will have seen all the warnings that you will get if you still use the security manager in these past releases. And as you move to 24, nothing's going on anymore. If you're not going with every 6 months release, you might not have noticed this. You might not be aware of this. And as I said, this could technically happen on your behalf. So if you are at this point, you shouldn't be on any release between 12 and 16. If you're on 17, then you have this option available to you, java.security.manager equals disallow. You should absolutely run your application with that, and then you should say, it works, good, I'm not impacted. And if it is impacted, then you should move away from it. So this is your way to prepare if you're not going to go to 24 anyway. OK, that was the one thing I want to tell you about in detail. They're going away. But then also we have a bunch of deprecations going on for removal. Deprecations in general just mean use is discouraged. There are many reasons why use of something could be discouraged, but deprecations for removal, it means it's discouraged because it's going to be gone soon. And most of these things, again, just like Security Manager, most of these things you're not relying on. There are a few things here like the allowed by default stuff, where JNI and dynamic agents, they're not going anywhere. They're all good technologies. You can keep using them, but you will have to add a command line flag to make sure that you accept the integrity potential integrity hazards that come with that. If you go through those JEPs, they will tell you all the details about that. Finalization is going away. That is an old-style way to clean up resources after you, which again, you're probably not doing. You're probably using try with resources, but your dependencies might. There's flags that you can use to simulate a world without finalization. Finalization, I think, was estimated by the DGC team to cost like 1.5, 1% overhead for the GC because they need to keep track of all the objects that are going to be finalized at some point. So that's good that that goes away. Primitive wrapper constructors at the very bottom are probably going away, not sure yet, due to Valhalla. So there's a lot of stuff going on here. You're probably not using, as I said, many or even any of those, but it's good to be aware. It's good to look through this and to check whether you're exposed and if you are to change that. Okay, that was the part we had to get through. Now is the optional part. We have like 13 more minutes. I have slides on all of this. This is not everything I could technically talk about. There's even more in preview right now, like compact object headers, but I felt I have enough content for the remaining 13 minutes, so I didn't feel like adding even more. But now it's up to you. And we're going to do like a first come, first served kind of thing. So whoever finds the courage to yell something so I can hear it gets to pick the topic. So what do you want to talk about? That was clear. String templates. Okay, let's go. Let's go string templates. Right, so let's go a little bit towards string templates, and then I'm going to tell you where it's going right now. So the idea is that composing strings in Java is kind of cumbersome. If you do this, you have a property and a value string up there, and then you want to create this select query, and you have to put in like string concatenation, or you can use string formatting for that. That's all very cumbersome, and also it comes with free SQL injection tag, so that's not great. Wouldn't it be great to do something like this? This syntax is not entirely made up, because if you know about the string template proposal, you know that the / curly brace is something that we actually see. But basically what I'm saying here is I'm just embedding these property and value variables here. The code highlighter doesn't recognize this, but this is the reference to a variable. And then I just get a string that has these variables injected. Now it's so much easier to get your SQL injection tag. So that is decidedly not the path that Java wants to take, because this is making the wrong thing easier. So no, we're not going to go there. Instead, to fix this specific problem, the path was taken elsewhere. And it's not just SQL injection attacks. That's the most obvious thing to do wrong here. But in general, all of these formats, JSON, YAML, HTML, XML, whatever you want to generate, most strings we generate in an application are actually targeted at another system, so it's some kind of structured language, and all of these have rules. Validation, sanitization, all this is format specific, and Java, the JDK, really doesn't need to know about all of them. It knows about XML, and that's all at the moment, so like JDK doesn't need to know about all of these. But whoever does know about these should check them. So if you want to create a YAML string, then you should have a decent and eloquent way to say, this is a YAML string, please check it for being YAML-ish. So the way that this was proposed is this. This was the preview in Java 21 and 22, where you would have here, I'm using a text block, but that doesn't matter. The proposal did work for text blocks and for regular strings. I'm using the / curly brace to embed variables here, and then I put something that was called a template processor at the front here. This SQL dot is what's called a template processor. It takes the template, and then it processes it, and it spits out something. It could be a string, but it can also be a domain object, which I found really cool. So this would spit out a statement, a java.sql.statement that you can then run immediately. Because why first validate the string, which includes parsing, and then making it a dumb string again, and then later give it to an API, which then has to turn that dumb string by, again, parsing it into a proper statement. So instead, this can be done in one flow, which makes it, as I said, pretty eloquent and safe and straightforward to use. But it introduces a kind of special syntax that Java doesn't have so far, right? It does this SQL dot thing here, which is a shortcut for SQL, which is just, in this case, a static import of a variable. It's just an instance of template processor. And usually on something like that, on a function, for example, you call it .apply. I'm not sure, I think it was called .process. So instead of calling SQL .process, here's a template, which is longer, and then we're getting, the Python folks are going to make fun of us again. So this would be more elegant, right? Because, I mean, jokes aside, the goal here is to find a solution that is more elegant than regular concatenation, so you use it, and then when you use it, you pick the right template processor, and then you get the safer and more expressive outcome, right? If this solution is more complicated than string concatenation, then those variants already kind of exist, and you wouldn't probably use them. This is still a little bit better because it's embedded in the language, because the / curly brace would still be there, so it's better than homemade solutions. But still, right, you could see why it would be nice if this is very compact. And so this special syntax was introduced for that. Also, for performance reasons, because then, well, I'm not going to explain why, because it actually turned out not to be the case. So this just special syntax was a bit too much, right? So it didn't carry its own weight, so a decision was made, you know what, let's pull that back. So they were removed from JDK 23, and now the feature is going to be redesigned, and I don't know when that will happen, which makes me kind of sad because I really like them. But it's important to understand that if you ever heard like, oh, the backslash curly brace is so terrible, good thing they retracted that proposal, that part is likely going to stay. That's not the reason why it was retracted. That's just bike shading over which character we prefer more, and backslash curly brace has a bunch of reasons for it, so it's probably going to stay that. I want to say, with my limited insight, it's surely going to stay that even. But the goal is not code growth. The goal is to find a solution that makes it safer to produce things like SQL statements or JSON documents or HTML documents from a string in a way that you can rely on all the validation having happened. So that's the redesign. The redesign is not bike shading over the syntax. The redesign is getting to this goal of safety and reliability in a way that does not introduce this special syntax. There's a mailing list discussion about this. So if you do feel like you want to, form or deepen your own opinion, or if you even think like JDK does these things, OpenJDK does these things off the cuff, I invite you to read that mailing list discussion. It's super long and detailed, touches every topic at least twice. So there's a lot of insights and different opinions to be had on that. And I'm thinking Gavin Bierman, who's I feel in charge of this, is probably going to meditate over that a while. And then I'm hoping we'll see something. I'm not sure whether we see something this year. Again, I wanna, but that doesn't mean that much. Everybody's busy, so let's hope we'll see something soon. Does that clarify the string template thing? Also, we should see this, by the way, as a win for how the preview feature system works, right? We have introduced preview features, or OpenJDK introduced this concept of preview features, so things can go out there, can be tried in practice, can gather more feedback. And one of the feedback was, what's up with this weird SQL or whatever syntax? And so this should not be seen as a failure on the behalf of string templates, but I would say it's a win on behalf of OpenJDK's process, because it means it works to put things out there, gather feedback, and then, if changing it isn't, like, if it's not a quick fix, but it takes more to work to fix, then let's retract it and let's fix it later, calmly and in quiet. Okay. I think we have time for one more. Let's go all the way back to this list. No? Do I have to? Primitive patterns, and GGC. I heard GGC, let's go there. That's super easy, and then we go to the primitive patterns and see how far we get there. Generational GGC, quickly explained. What is GGC? That's a garbage collector that optimizes for ultra-low pause times. Ideally, you have a collector that has no overhead, no pause times, and you can have that. That's 0GC, but that just crashes when you run out of memory. So that's going to do not good for your, what's it called? The one that doesn't do anything, it crashes? Epsilon, right, sorry, yes, the name is Epsilon. That's the garbage collector that doesn't do anything on purpose. It's for benchmarking reasons. So yes, so you can have no overhead, and you can have no pause times, but you also want to have throughput. So Epsilon is really terrible for your throughput since it crashes when you run out of memory. And ZGC says, okay, what we want to optimize for is pause times, because we cannot actually have a garbage collector that has like 0 in all of these categories. You need to make some kind of trade-off. ZGC says pause times is the thing that we're focusing on, and that means it can have a higher memory footprint or higher CPU usage than other garbage collectors. So for example, parallel GC is better than those last two, but it can inflict like seconds-long pause times on you, and if you have users on the front end waiting, that's not great. So GGC is something, if you care about the 99th percentile of your web app, you should totally look into this. In JDK 21, GGC became generational, which means it's leaning on the generational hypothesis that most objects die young and those who don't grow very old. So it makes sense to keep all the young things around, like in the kindergarten, and then kill it off, like not in the kindergarten. And then I have all the old ones in a retirement home where you kill it forever. And you do this by tracking young and old generations, or if you have a regional garbage collector which has regions, you say this region is the old one, this is a new one. You can go more into details on this. ZGC didn't do this, but it can do it now. And this is some out-of-context numbers that I stole from a Netflix blog post. I highly recommend to follow up on that link if you care about this. I just want to give you an impression that this works, right? This is not a guarantee that you will see the same, but just an impression that it works. The gray block here is history, and the blue is current numbers, and then here they went to generation ZGC. So you can see here a 5% improvement, roughly 5% improvement in, I think, live set size. So memory reduction, right? So that's good. And then here, they recorded pause times. That's pretty impressive. The graph doesn't end here. The numbers just go so short to 0 that it doesn't show up in the graph anymore. So they are super happy with that. As I said, read that blog post. That means for you, if you care about these kinds of performance characteristics, you should definitely give it a try. The generational mode was introduced in, I forgot when, I think I want to say 21 right now. It became the default on 23, and on 24 and plus, it's the only mode that still exists. So on 24 and plus, you would say -XX : plus use GGC, and then you would get generational mode. If you are on 21 and you want to experiment with it, you can look up the JEP and it will tell you how to activate it on that. Just to be sure, G1 is still the default garbage collector. So ZGC optimizes for ultra-low pause times. Parallel GC pretty much optimizes for throughput. And G1 is a little bit of both. It sits in the middle. That's why it's a good default. Depends if you have super limited hardware, you actually get a different garbage collector, but in most machines you will get this one. So G1 is a good default, and it will stay the default. ZGC is the one that just got its generational mode as a default now. And more content. The first JEP is the one that introduced generational ZGC, so you can take a look at that and how to activate it. JEP 474 is the one that made it the default in 24. Then more articles and blog posts, and videos about that. And then we're going to go to primitive patterns until they drag me off stage. Where is that though? Let me see. Oh, it's a preview feature, right? There we go. Okay, primitive patterns. That was the one that was requested, right? I heard that right? Yes. Okay, good. Let's talk about primitive patterns. Okay, so in instance of checks and in a switch, pattern matching can match against reference types, right? So you can switch over something like a user now or something like that, right? Like a complex object, not just strings and numbers. So you can match against a reference type. You can deconstruct records. You can nest these patterns in one another. And with the underscore, you can ignore certain parts of a pattern. And in a switch, you on top of that get the selection with guarded patterns, which is the when this and that property holds. So this is what patterns offer so far. And I would say that this plus the sealed types are what I call the pattern matching basics. This is what you need to start using pattern matching in earnest. You got all the features that you need to make this work, and I've done this in various internal projects. I'm having a lot of fun with that, so it's really cool. I can only recommend to look into that. And now it will be built up with more features, but it will also be built out to rebalance the language. And this is where the instance of where primitive patterns come in. So X instance of Y used to mean is X of the type Y. This is how we read instance of. Right? Is the variable X of the type Y? And we should really change that perspective and think about it. Does X match the pattern Y? So does X match the pattern being of type string or being a record that can be deconstructed thusly? That's how we should think about it. And for the old semantics, asking is a long an instance of integer is stupid, because of course not, it's a long, right? So since there is no polymorphism involved, this question didn't make sense, so the compiler even forbade that statement, because it was a categorical no. But now the new semantics are, can this long match an int? And then the answer is, yeah, if it's in the right range, it probably can. So that's basically what's being introduced here. So let's use an example. I have a number 0 here. The question is, can the number be an instance of byte? Looks like it, right? It's not an instance of byte because it's an int, but can it be a value of byte? Can its value be a byte? Yes, because it's 0, 0 fits into bytes. So this is what this will look like. I create an int, and then I say if an instance of byte, then claim it's a byte, and otherwise say, well, apparently it's not a byte. And there are more checks. I'm not going to talk you through this because I will be booed off stage. What's special about this number? The special about this number is it's the smallest positive int that float cannot represent. So this gets funkier because does it fit into a byte as a regular range check? But does it fit into a float precisely? It's no range check anymore. That's more complicated. You have to do like double casts and figure things out. Or you just do this. You just ask, is that number instance of float? If yes, you can use it. Otherwise, you can't. You can do stuff like this now. If you always use tri-state booleans because they're more fun than just regular, binary booleans, you can switch over a bool. And if it's null, you do something. If it's true, if it's false, you do something else. There's a bug in 23, but it's fixed now. And then there's more on that. I go into details on restoring the balance with primitive patterns in that video, but as always, you can read that JEP. And with all of that said, I think I'm done. I want to thank you very much for being here. And I want to tell you, do go to the to the Java YouTube channel. Don't go to the Oracle. Go to the Java YouTube channel. Also go to insight.java or dev.java, depending on whether you want to watch Java evolve or you want to just learn how to use it. Thank you very much. If you have any questions, I'll be around. You can probably spot me. I'll be at the Oracle booth. I'll be here right after. So yeah, have a good conference, everybody. Last day of JFocus. Make it count.